We have discussed the idea of kinetic energy in terms of an object moving in a line. This idea of kinetic energy related to an object's mass and its linear speed v will still be useful in many situations, but we also need to include the energy that something has based on its rotation, such as this gear that is rotating about a fixed point. Even though it doesn't actually move through space, there is certainly energy associated with this rotational motion. To calculate rotational kinetic energy, we do something very similar to what we've done with other formulas based on linear ideas, and that is to transform that equation into something that deals with rotational ideas instead. So with rotational ideas, it's not just the amount of mass, it's how that mass is distributed that matters. And so we will use I instead of m. And it's not a linear speed, it's an angular speed, omega, that we would be looking at. So our kinetic energy formula for rotational motion has the same exact form as for linear motion. It just uses ideas more related to rotation. Now, it is certainly possible for an object to have both of these types of kinetic energy. For instance, when a tennis ball is hit, it is not going to just move through space, it's going to have a spin. And so we would need to take into account both of those types of motion. As the object translates, it has a linear speed v, but as it rotates about its center of mass, it would have that rotational kinetic energy. So you should expect to use both forms of energy when you are asked to calculate the kinetic energy of an object that translates and rotates. It's also possible for this idea to be taken to a special case where an object is both translating and rotating, but there's a specific relationship between those two motions. This is something we'll look at more later this week. But in that case, it turns out that there's a very familiar looking relationship between v and omega. It's that the linear speed v of the center of mass is equal to r times omega for the rotational motion. And again, this is going to be something that will be true for an object that moves through space and is rotating, but does it with contact with a surface so that it rolls without slipping. Let's take a look at an example of how to use the rotational version of kinetic energy here. So you can stop the video for a second and jot down the problem if you'd like. So this problem talks about a disk. You know, when we see that phrase solid disk, right away we should be thinking of the formulas that we have been using the last few weeks. And it talks about this disk rotating about a fixed axis. So this object is not translating, it is only rotating. And therefore, when we go to calculate that kinetic energy, it's just going to be a matter of the 1/2 I omega squared relationship. So there's a few things that we'll need to do to prepare the information for substitution into this formula. For one thing, we are going to need the value of I because I guess it doesn't really specifically say this, but the fixed axis, let's assume, is through its center point like it usually is. And so our formula for I would be 1/2 mr squared. The diameter was given instead of the radius, so we'd want to make sure we cut that in half, and we end up with our inertia value, you know, pretty small, like we should be getting used to. We'll also need the value of omega. It was given to us in revolutions per minute, which is not our standard unit. We need that magic unit of radians that can come and go as we need it to, and of course in seconds. So this converts to 18.84 radians per second, and then it's just a matter of putting that into that rotational version of kinetic energy. Rather small value, 0.53 joules of kinetic energy. Right, well, let's take a look at something a little bit more complex where it has both forms of motion. So again, stop if you need to jot down the problem. When a soccer ball is kicked, again, very likely that it would have a rotation to it. A lot of players use that rotation to their advantage, but this object is moving. This ball is moving at 12 meters per second through space at this moment, and it's rotating at 4 revolutions per second. So again, our goal is to use both forms of kinetic energy to find the overall kinetic energy. Um, but we'll have to do a little bit of prep work with the information given. So um, in order to use this formula, we will need to figure out what the radius is. We were given the circumference, and so we can, use the c equals 2 pi r or the pi diameter formula and determine that the radius is 0.108 meters. Notice that I put that 2 pi in parentheses. Be very careful when you do this calculation that you group the 2 and the pi together when you divide so that your calculator gives you the result you expect. All right, the soccer ball is being approximated as a hollow sphere. So the formula for that is 2/3. Oops, wait, I guess I did the the rotational speed first. So first of all, the rotational speed is 4 revolutions per second. That's almost the right unit, but we do need radians, so we'll just convert that portion of it. So our 25.2 radians per second. Okay, and now we'll go ahead and calculate our value for I. Okay, this is considered to be a hollow sphere, so that would be 2/3 mr squared. That's why we needed that radius value. And we can go ahead and put in our mass and so forth. And again, a pretty tiny value for inertia that is common for everyday objects. All right, now it's just a matter of carefully putting things in and plugging them into our calculator. Be extra careful as uh, square things and so forth. But overall, our kinetic energy is quite a bit higher than that first problem. But of course, we're kicking a soccer ball, so it's gonna have a fair amount of speed. You might ask, well, how much of the energy really is in that form of rotational energy? Because last year we would have ignored that entirely. Well, it doesn't turn out to be that much in this particular case. If you just calculate the rotational part, okay, it ends up being about 1 joule. So most of the energy, 29 joules or so, is in the form of the linear kinetic energy. It is the translation is about 97% of the energy. So maybe in this case, it would have been okay to not worry about it if I was just trying to sort of figure out where the ball would go and so forth. But in other situations, it's going to be very important to keep track of both types of energy.